Okay, let's move on to our second effect, which is our particle effect. Here we continue to create a new sphere. Change its sharing model and use our polygon. The wiring is relatively evenly distributed. We also gave it. After that, use our mountain node. This time, let's go. Because our emission source is very small, it will be very small when the time comes. Then, when we are our transmitter source, we can actually try as much as possible. It is somewhat irregular forms. Then you can also pull it up here. We can add a subdivision to our model. Segmented mode, we proceed to choose our loop mode. It is currently such an irregular spherical shape. Next we go to give our ball to do some areas. It's like in CCD. We go to draw some vertex maps on a model. Then let this vertex map emit the particle. In this context, our thinking is actually the same. Here, I use point warp. What kind of node is this? If we take some of the actions we are doing now, such as making a car or building a car, then we can think of our point warp as our front of the car. What is the front of the car made of? Inside it will have an engine, and then various sophisticated instruments that run it. Then this point warp can actually be understood in the same way. We see our hull as the front of a car. Then let's click in. It has some functions inside. These functions are equivalent to the engines and parts inside our cars. So many things are organized together, and it becomes a complex engine for us. After the car cover, after it is covered, it is equivalent to returning to the outside. It looks very concise. Then open our interior. In fact, we have carried out some various sophisticated operations inside. Open our dung, car, and pick a Mercedes-Benz car. Okay, let's find out what it looks like. We think of the head of our car as a point warp for us, and that's where we see it. When we open the hood, you will see the engine compartment parts, like the engine, the internal combustion engine, these things, all kinds of parts. Inside point warp, it has a lot of these functional stuff, and it comes together. It can be combined into some things we want, some things that we customize. It has a very complex structure inside, so we only need to briefly understand some of our commonly used functions. Then look at its name and know that it is to do some operations on the point. Okay, let's come in. So how do we make one of our masks? We can use our noise, so here I chose a noise. We connect our P to our P, and then output our noise to our CD. CD is a meaning of color in Houdini, and the attribute of color is CD. Uppercase C, lowercase t. Then we connect our noise to our CD and we can see our model. It actually has some changes in black and white. Give us the interface and add our geometry spreadsheet. Then this is a very important page in HUD and GNI. Let's see what data and attributes are on our model all from this side. Then you can see that there are P, X, PY, PZ here. Each model has a point corresponding to where the coordinates of the world are. Then on each point it has a CD attribute, and that CD attribute has RGB. So there are 3 components, so it's a vector. Then I think my emission source, I want to make it wider, but not as big as the area. Then we can adjust our frequency, and by swiping our frequency, we can tune to the one we like. Here, I think the black area is too close to the white one. There are fewer white areas than black areas, giving our black and white a contrast. A gradient is added to make us have more and more black areas and fewer white areas. Then there's a node here called fit. Then we connect it to it. We can judge it according to the value. Then we value it, and the minimum value of the source is 0. The biggest possibility is 0.40 minus 3. We can give 0.5 here, show everyone. So from 0 to 0.5, we map it to 0 to 1. It is equivalent to widening our entire range. So what is one of the results we want? One of the results we want is to say, what about the white? We want to keep it too, but not so much. Then we will increase the minimum value of one of our sources. That way, as our value gets bigger and bigger, it will be mapped to 0 by default. Then through this, we can pull the contrast and make our white areas more visible. You can see that this is now a launch area for our white. We can continue to adjust the parameters to the shape we want. You can also continue to adjust one of our frequencies. I think it's okay, so I want to play it through time now, to think about how we can have some animation in black and white. Then at this time, you need to use a time attribute. Then here I use vector 2, vector 4, V to V. Because our noise is a 3- dimensional data. Add time to it, and it becomes a 4- dimensional one. So we need one that converts 3D data into 4D data. Then this node plays this role. We connect our time to our port below and connect our P to it. Then the whole is given to our P. Let's bring back one of our previous frequencies. We can go and swipe it. The flash is fast because it is fast. We can pass a multiply node. We can pass through a multiplied node. Give us speed to multiply by a value. Then we move our mouse to the second port. We press the middle button. Tap promote again. This way it will extract a parameter to the outside. This is one of the speeds that control us. Then let's double minus click on it again. It pops up a note. Then here we can change its name. Then we press U to jump to the previous level. You can see that there is a time scale here. No, it's 0. Let's play it and take a look. It didn't move. Let's give a little value. You can see that it starts to animate a bit. Since we can extract our value to the outside, can we also mention the outside of our size? Then we can follow the previous method to use the middle mouse button to click. Then you can also go through the panel of this parameter to click on this pinion. Let's click. This way, it will be extracted to the outside. Of course, you can also go here and double minus click on it. For example, let's use the one on it. Then we can change it here. Okay, let's do some spinning animation for our madness. Here I will first tell you how to prescribe some needles during activities. Okay, let's choose our transform node. If I want to animate this axis of rotation, let's zero it first. We will use R. We hold down our key. Go and click on the parameter we want to change. Let's click. You'll see the sign turn green. Green means it has a needle. Time to our 50. We give it a 10. Let's click out again to click. This case is done. It has 2 needles. And since we all use Houdini, so is there an easier way to do a simple animation like K? Because I just wanted to have a numerical increment on each axis right now. A linear animation. Let's cancel our K needle first. You can right minus click here. Then find the delete channels option. Let's click. It will give all the keyframes. There is another way that is faster. It's a shortcut. You hold down Ctrl and Shift. They cancel my reference. Good. Here we go to program a track like controller. We give our spin to Andra FF. Here too, F, when entering some variables similar to our expression minus specific variables. Be sure to enter it in the English input method. Then, here F is capitalized. You can see that it has also turned green here. Then, let's play and take a look. You can see that it has already turned. So what does FF mean? We can click on our channel, then swipe our keyframes. You can see that it corresponds to our timeline. That means getting our current frame. Okay, now with our launch area. Then our launch crew animation is also done. Then go sprinkle it a little. We use scatter. The default scatter will be for all objects. That's not what we want. We want a property that we create in it. That's what I'm giving now. Then I want to give it here. Because CD is a built minus and a rebuild of the system. We want to use a property that we define ourselves. Easy to call. We export a bind export through this. This is deriving a property. We give it a mask. That type is floating minus point numbers. This is equivalent to creating a new product called mask. Is a property of floating minus point numbers. You can see this one of ours. There is a mask here. Each of them has a different value. Come out of the woodwork. Back to a scatter. Then there will be a density attribute here. It means which attribute do we use to sprinkle points? That here. Give us a mask. You can see it on our math. So, why are there some black ones? That's because the value of black is not 0. It will also have a little weight, so it will be scattered. This one doesn't matter, because we just want it to be sprinkled in this area. Good. This is who we are. Give us a spin to take a look. In order to enrich our emission sources, we can give us random seeds of scatters. Also give it FF. This makes every frame different. You see, every frame in slashing. In this way, the emitted particles will not look uniform. Okay. Then, one of our transmitters is already halfway there. We're going to give our particles a lunch. In Tiger Jenny, do some particles. It requires some of the most basic properties. For example, speed B. CCD or other software gives some default modes. There will be a speed. Good. Let's go into our CCD to see how the particles in the CCD emit up. Then I will build a new transmitter here. There. Let's click play. Then it will have particles emitted forward. So I do particles launch forward. That's because it has an up minus and minus velocity. Its speed points in the direction of the z-axis. We can take a look at our parameter. Find our speed. You see it has a value of 150 here. Then our orientation towards z. Then we can change. For example, let's say we are moving towards positive y. Then it is up. In CCD it has a direction of speed into speed size by default. The direction of the speed is according to our axis. It judges the direction. What about the size? It is based on one of them. That is entire length 0. Because it's something very low. It takes a lot of things that it doesn't encapsulate into a single thing. What about the process of learning Tiger length 0? Many things need to be built step by step by step by step. And there are several benefits to this. The first is to deepen your understanding of some of the underlying operating logic of 3D software. A principle to understand. Another benefit is to help you get familiar with the software. When your knowledge grows, you know how things work. You can better control certain things. So the more you learn this knowledge, The more complex effects you do later, the more helpful it will be. Because many things are the principles of how you disassemble them step by step. Okay, then the speed will give us 0. You can see, then it didn't fire. Right. Okay, then let's go back to our HUD and GNI. Then, we just found out. Then, we emit particles. We need the basic steps. The first step is the second step. It is to get a speed magnitude. Let's take a look at our ball. Click to our penultimate one. It is similar to a kind of sex. This makes it easier for us to observe a general pattern of the current node in the node above. What we want to do is let our particle diverge towards the outside of our sphere. Then, this is obviously to diverge according to our normal. Then, just let our speed be equal to the direction of our normal. Isn't that okay? This is the first one. The second is to get a numerical size of a speed. Then, we need to go to scat to do an operation. We add our normal node. We can directly add our normal to this piece after the subdivision. Then there is a display normal here. We clicked. You can see. This is one of its vertex normals. Let's go and change our normal to our point. You can see that the normals are almost perpendicular to each of our faces. Now the direction is to unify. I want it to be a little different in size. The direction is also different. It feels a little like making waves. For example, it may not be perpendicular to its side. There may be a slight deviation. Then our normal is like this now. Generally speaking, we set a value of velocity v. That is commonly used in fixing forces v. What about 10? It just represents a normal. We do this to avoid duplication. Then, we usually convert the normal into 1. Then here we need to use a 1 go. That's actually very simple. We just need to type v at e v at n. Let's enable get edit block. We turn off our normal display. Then, we move our mouse to our node. We can see that there is a change number here. That's some information about this node. Let's click a bit. An interface like this will pop up. Then this interface is convenient for us to check various attributes. Then, we just went to a V property generated by n. Then, let's stop on our V. If you click and there is no response, then you may not be able to use this piece. This piece is to visualize our attributes. You can see. Until then, this was our n. We can see it with the right click. N and V are almost identical. It's just that the length is different now. That can also be changed to we right minus click on. Small pencil. We can change our length. You can see. It's actually exactly the same. Now let's look at whole V. It can be seen that it is actually relatively unified. For example, one of its lengths. Now we want to make our launch sources richer. Then you need to do something about this V. For example, I want it to be different in length. The size is different. So let's take a look at the example we launched. Isn't it that the form will be richer? Spreadsheet. You can see that VIT is also a vector. It has 3 values. Then we have to use that. And we build a just vector. Let's take a look. Then we have to adjust it. Then you can see that there are 3 patterns for this. One is to control the direction and length. One is the top control direction. One top controls the length. Then here we can control it separately. Take control of one of our directions. Change our pattern to 1. Change to 1. You can take a look. You can what? Let's change this size of ours. Let's make it smaller. You can see it in the modulus of the tuning up. Let's change it a little smaller. Then we can choose the mode here. That's the 0 center. 0 as a center. Then there are positive and negative. What about min and max? Obviously, there are big and small. You can control. The big is straight and the small is straight, according to your preference. So here I use a 0 center. Then give it a little straight. Make it a little different. You can come back and take a look. This is what we started with. This is one direction we are in now. It's a bit disordered. Right, good. Then we will add more. We can hold down the Alt key, copy it. Let's put it below. Then this time we change one length of it. Then we can use one here. Random. You can see. Here we can use a set mode. We set our entire set. It is only 0 to 1. Then we can give it a little. This can be used to increase our value. Then it is big and small. Good. We can add one more. Then here I want to do a general control. The whole controls one of its sizes. You click here. We have one size that controls one of our lengths. Then here we change it to multiply. Any number multiplied by 0 equals 0. Then if we become 1, that's the pattern just now. Then if we can enlarge this, we can adjust our values very high. Good. Then this is the one that controls us. Direction. We can give it a name. Understand too. Direction. Then it is one of us that controls you. We can big. Good. That's how big we are in total. You can watch. It can take each step apart. Very convenient. In the future, we will refine and adjust every place. Good. Back to our scan. You can see. Our points are also counted. Properties above. This can be seen. This point will be towards it when the time comes. Some of the directions are now being pointed to. Go launch. Turn off our properties. Good. Now ours. Then we can get into one of ours. The simulation of particles. Empty nodes. Okay. Sort out our nodes. What about particle simulation? Mainly used top network. Butterflies and butterflies. One that specializes in simulating particles. Solver. Then it has been given to us. Built one. Subassembly. That's like TopNet. Belongs to the DOP. DOP. You can see, there's one here. DOP is in us, butterflies and butterflies. Go to the simulation one. We jump out. You can see. Then this is called DOP. Good. Then here it has gone by default. Something for us to build. We don't need to go. Don't. Build it yourself. Good. Let's come. Let me explain briefly. What about DOP? Mixer. Then we are outside. What about these settings? It's equivalent to some raw material. Then a blender. We put the raw materials. Pour into a blender. Do some processing. Become some ingredients. Pour it into the tying machine. Fry it. That is now possible. Put the DOP. Run. Never. Just this one that fries apples into water. Process. We need to get to the right point internally. Do a few things. Good. Let's take a look at one of ours. Pop source. Then this is our source of emission. The default way it is sprinkle some dots. Sprinkle dots on the surface of the model. On my side. Because we have already dealt with it here. Then we just need to use these particles. No. That's it. Use one of our. This source. We choose the first one. Then we will take ours. Emitter. Press C. Copy it. We paste here. We are done pasting. You can see that we already have this interface. Let's play it and take a look. There are particles emitting. Then we can put this. The display grid is cancelled. Then, now, it's already launched. So what is one of our effects? It's our ball launch. Launch our particles. Go and hit the ball outside us. Generate some collisions. Inside to shape some launches. Good. We jump back. Then we will go to the collider. The collider. That's our ball. That's generally speaking. To summon Houdini. This collision. We mean process its data. How does it process data in Houdini? That's what it takes hours. Go convert into a VDB. By VDB, go to roughly gather and disperse one of it. A boundary of the model. Collision through VDB. Then we will use one here. See leasing source. We came over. Then it has 2 ports here. We can put the mouse. Move to the unit on the left and take a look. It will show what? The output is goo. Let's take a look at it with a space chain. We give it a name. Capital goo. It showed up. Then this is with us. The model above is exactly the same. What about this way? Point and look. It will write a VDB on the side. Then, what it outputs is VDB. We also use a space chain to express it. We give it the output of VDB. Good. By default, it already has an effect. That goes through here. You can change one of its sizes. It defaults to 0.1. Here we have smaller numbers. The more precise it calculates. Let's give it 0.70 minus 5. You can take a look. Not obvious enough. Then, give it 0.0. Good. Can be seen. Right. That's because we don't really need it in this case. Such a fine model. I give it a 0.5. That's it. This is more resource minus saving. You can see, it goes in the form of a VDB. Then, R2 important data. To this node. One is goo. One is VDB. Good. We enter one of our bubbles. Use collision. Of course it is. There's a collision here. Stay object. We use our mode. Okay, take us outside. These 2 pieces of data are important. Then, here I give it. Make one. Partition. We double minus click it. Give our window a pin. Our side in fixed at 2. This side is fixed to 1. We double minus click in. Select towers. Collide. Select our collision. Then this side is routine. What about the process? For our goo, give us the SOF column. What about VDB? Then let's choose our mode first. Each volume mode. Then drag our VDB in. That's a proxy model. Good. Here you can. This shows our VDB. Follow us to close our VDB. Let's play it by default first. Good. There's no effect, right? You see the fault here. Then we want our particles. There is a collision inside our ball. Then here we have check this input sign. Okay. It collided right inside our ball. Let's look at this pattern. We are now launching sources that are too big. Then our effect is not very good. We need to keep our emission source small. We narrow down our emission source. Let's give it 0.1. Let's go into one of our pop nets. Let's go launch again. Good. We can see our particles emitting in bands that hit our ball. Actually, I don't want this part to bounce back. Then we can make it a lifetime. The point that bounces back may be dead. Then choose our pop source. We find a value related to lifespan. Here it is. We see a life. Then, let's change it to 1 first. Let's take a look. It only takes 1 second to fire. 20 minus 5 frames. Then let's give a 3. You give it a little more slice shift value. Let's say give it a 1. Then it is from 2 to 4. Because it will. This value is a random value. It will be added and subtracted according to 3. Minus is our minimum. The addition is our maximum. So 2, 4. It is not enough to be seen. Then we continue to add our lives. We give it 3.5. Let's play again and take a look. Give a little more. Give it 4. Good. This is a state. Now we can see our emission source. There are too many places where it launches. I want it to launch in this area. Jump out. Go and change this. Then this is change math. Then let's go again. Let's change ours, for example. Red and dry our part first. Change our frequency. We make it a little less contrast. Tune it up. We do it again. Go back to our partnet to watch it. Launch it and take a look. Such. This pattern is... I think it's okay. You can see it. There are not so many emission sources. It's still okay. That is current speed. I think it's a bit low. We can increase the speed of it. Then come back here. Go and speed up. The human body is enlarged. Then let's say, let's give it 10. Let's try to take a look at it again. Then it will be fast. Right. Then our particle description can also be slightly reduced. Can be given a 3. The whole process is a dynamic adjustment. Because of you. Just some parameters. Then other parameters maybe. Its previous value does not meet the effect we want. For example, this that. We think it's okay to launch. Then we'll give it some fun mess. Because I think it's firing too regularly now. That's right here. Just pop. We are connected. Then you can see a noise here. We give it a larger value. Let's say we give it 3. Let's take a look. You see, the particles we emit are very disordered. You can see that the squeeze just begins. Now, as it emits more and more particles, then the whole ball is filled with these particles. The shape is not very good minus looking. Let's disable it first. Let it grind for a while. Good. What we want to do is get our ball close to our edge. It produces some disorders. I don't want it to be disturbed inside that ball. It was according to the previous launch. Okay, so how to achieve this? NCCD, you may think that I give it a spherical J to control one of its parameters. In fact, it is the same in arc speed. But CCD is the one that makes these tools for you. Then we definitely don't have these tools in arc speed. So go on your own. Look at the shape of our particles. We particles. It is based on the central point of the emission source. Each particle is almost different. For example, when it comes to the outside, it is the farthest from the central emission source. The closer you get inside, then the closer it is. Features. There is another characteristic. It is that the speed of the particles is different, because we give a proper wind. There is an air resistance on this side. Then let's put ours first. We set it to 0 for wave creation. Let's take a look at it by default first. This is the same as we were at the beginning. We give this air resistance. We give 10. When it was first launched, speed is maximum. The more you go outside, over time, you look more and more outside. That buffered the same. This is also a feature of it. Then here we can use our speed. Make a definition. For example, when our speed, when it is greater than a certain value, it does not create disturbances. That's less than speed. Disturbances occur when it is less than a certain value. What about this in general? The most convenient is to use our racks. Go and dry. Then, let's put our resistance first. Set to 1. Good. This is the default. We give one effect of 1.5. You can see that it is very stable. That enables one of our vacs, according to what we just said, to find the magnitude of our velocity value. Then 1 is your 0. Use a simple function. It's called an EF statement. That is, there is a parenthesis after the EF. It contains some conditions. When we meet this condition, we'll execute on our side a value in a curly brace. There's also an else in the back. That is, when this condition is met, it will be executed. Otherwise, then another paragraph will be executed. Good. then it is equivalent to us filling in the blanks. That's one of our verses. A v. For example, when our v is less than a 1. Then our string, according to what we just said, when our speed is less than a certain value, we wanted to produce some disorder. So what is this value? That's our intensity. So what is used to express the strength? We move our mouse over here, hover for a while. You can see there will be a blue pop minus up here. Then that's a value we call. Here we will write amp. For example, equal to a 2. After writing, we must add a semicolon. Then when our speed is less than 1. Otherwise, let's try it first. See if it works. Good. First of all, it didn't report an error, right? Good. Then let's click it and take a look. You can see that it is very flashy. That's because of our expression. It is true. Then there is a problem with our irregular writing. That was in Tigerland 0. We go call our properties. Then you must go. Add to call our property. This shows that we are V. That is value. The broken value is equal to 2. Otherwise, then this value is equal to 0. Let's see if it works. You look like it's working. Right. Let's see if it works. Let's compare. We tick off our vex. It seems to be effective. Right. We enable our vex. It works. But it is also irregular to write like this. Because of our vector. Because our VIT is a vector. In fact, we have to calculate one of its values. By this value, compare the size. You can see this one on our right. So we want to make this vector of ours. The value is a floating minus point number. Then we need to use a NAS function. We give it. So what does this function mean? We click our mouse on our function. Then it will pop up a help document. Show what this function is for. It says to return 这里我给了一个造波. It can be translated. You see the return vector size. Then you can see that it will have a float here. Explain what data type this function ends up with. It is a floating minus point data type. That's what we want. At this time, we will see again. That's the right way for us to do data. Okay, our effect has already worked. Let's go back to the beginning. Then we can see our side. It's a small piece that maintains this movement. Then let's go. Is it because our value is too big? Then let's take a look at it a little smaller. Let's give it 0.5. We'll give it again. Give it a little smaller. Let's give it 0.1. Okay, 0.1 is too small. Then let's give it 0.2. Repeatedly go to the test. 0.2 seems to be small. Let's give it 0.3. You have begun to make some changes. It can shorten our particle life a little more. Give 2. You can see where we are now. At the beginning, the transmitting source still maintained a default state. Then there is some disorder in this area. Then let's change our value again. Give it 0.20 minus 5. Good such a form. Well, that's an effect that we control us. It's close to our transmitting source. It maintains a previous launch form, where it was almost outside. Some disorders are generated. What about these parameters? Everyone has to adjust slowly, to adjust to a suitable value. Then it depends on one of your scenarios. Adjust the parameters and test them. That goes with the bubble. Let our particles slow down a bit. You see, there's already a sense of disorder now. We can put ours this. Turn up the speed a little more. Just give it 15. Let's take another look. This form is okay. Then there are fewer particles hit back now. Then we're going to give it. The lifespan should be slightly increased. Let's take a look at the point 2. Okay, this is okay for now. You see the emission source spinning. A central launch area. Maintain the original form. There's some disorder when you are about to get outside. Crash back later. Then slowly disappear. Okay, then let's do something. Some more refined operations. We don't want me as a particle. Now it's scattered. I want it to slowly move closer to our source. For example, the area where the particle density is concentrated. You see it's distorted now. I want it to produce some drawing effect. So how to do this? Let's talk about how to make our particle forms richer. I want my particles to fire now. There is no need for such proliferation. I want to get it closer to the part where we emit those particles. This will produce some convergence and drawing effects. In this way, we will see that the whole pattern will be richer. So what effect do we want to achieve? It is the part that makes our particles sparse. Go close to our particle minus dense parts. Like these sparse parts. Go close to the dense parts of the emission source. Like these areas with moderate particles. We also want it to go close to one of our emission sources. This will allow the particles to produce a cluster. Then, let's simplify our scenario. Here I represent the sparsest part of our particle in blue. The yellow area indicates that the particle density is slightly more concentrated. Then, red is the part with the highest concentration of particle density. This is one of its conditions. One is a vector that gets the movement of the particle. The second is to produce displacement. Good. Then, let's assume that each of our particles now generates a force of 0.1 with each other. Then our red area will generate a force of 1 on the blue area. Because we have 10 dots on red, the same can be obtained. The yellow area on our side will have a force of 0.5 on the blue area. That is according to the parallelogram below. Let's draw a rough picture. That's roughly the direction. It is a direction pointed to by our blue arrow. It will move closer to the piece with more force. Yellow creates a force of 0.5 on the red area. The red will produce a force of 1 on the yellow. Those two forces. The final result is a force that moves from yellow to red. Then you will see it visually in the end. Approaching red and blue will approach in the direction of red. Then we can draw a conclusion. That is, the denser the part. Then its attraction will be greater. Now, we have an idea. How do we achieve this step in Houdini? Then, we first need to get a density of our particles. So here, we have to jump to our outer layer to generate an attribute. We call it the density property. We also use one of our attributes. Then, we need to define an attribute. So I can tell you that this property is a float data type. The way to define the float attribute type is fi. Then enter your property name. Here we call it density, and then let's say we are equal to 1.0. Then open our spreadsheet. You can see that a property called density is generated for each point. Then the value is 1.0. Then you can also use this method to create. Create. Let's apply the name of the song we gave it density. Then you give it a 1 for this value. You can see exactly the same. Then let's use it for a while. You can see that the density attribute is gone. Then, here's this way. You can use it according to your own preferences. If you are a little annoyed or a little resistant to typing some code now, then you can use it. Then we directly use the bending structure of our HP. Here I deleted it. So why do we generate this property? Because we need to generate a volume based on this property. It's a body speed and we come in. So here we need to use some nodes in the SOP in the top. Then you need a node called SOP solver. SOP solver. We connect in. We double minus click in. Then you can use some nodes in our SOP here. Then the first node we use is volume west. We came over. That's according to what we just said. We need to generate it to our density property. Because we have defined it externally. Let's give it a simulation first. Now it's such a particle form as ours. Let's show our volume. It's big. We can change the particle size of one of our particles to be smaller. You can see that it almost roughly simulates a form of our particles. Then let's give it a little lower parameter. Then it will tend to be more of a volume of ours. So here we need to make our volume a little bigger. This way, we try to encompass our particles in the volume we generate. This way, some particles will not be so small because the number is too small. It is not included. It may not be detected. Okay, then our volume is there. Then we need a vector now. So how do we generate a vector through our volume? you can see that our density property is a 3 minus value. Then image is VDB here. We connect it to use the grid NT pattern. Then this model will work on us. Because we use the density attribute here, then it will generate a T minus degree value based on our above property. The T minus degree value means that we have a small density. We also have places with a high density. That will produce a vector in such a direction as a direction with a high density. That's a vector value we get. Then this is one of our density values. Okay, now we have vectors. Then let's do something with our point valve. Connect one of our generated vectors to our second port. Double minus click to come in. Then we need to use a node called volume sample. We use the volume sample vector. Because we're sampling the sample data, we want to sample this vector. As the name suggests, this volume sample vector, that's sampling. So here, I open the windows. We can see that the VDB analyze connection here is our point, VAP second port. Then, what we want to read is this generated vector of our second port. Then, we're going to connect to our second port. What about the location of the sample? That's our P. That is according to these particles. Sampling is done based on the particles from our first port. It is generated through our particles. Then this node defines us by the position of this particle. Okay, then here we have to give us a direction to carry out normalization. Let it be 1 in length. Then our particles create a displacement. Just add the position of one of our original particles. That would allow it to produce some displacement, because we already have our direction vector now. Okay, let's take a look. Directly to see if there is any problem. Okay, something is wrong with it. Did you notice that it was shaking a lot? That may be because the value on our side is very large. Then, let's change it to a smaller one. Let's multiply it. Name it scale. We give it very, very small values. 0.1. Let's take another look. It's too small. Let's make it a little bigger. 0.0. 0.1 look. You can see that it has an effect. Again. Let's take a look at the effect. Sounded like the effect of convergence and proximity. Let's check it out. Are we wrong in some places? Here we have the wrong sampling position. We should give us a sample. Okay, let's take a look. We give our value a little more. For example, 0.1. You can see that the free particles outside of us are getting smaller and smaller, but outside it will become less. Because our grain is too big. It is all close to our transmitting source. Then we have to rely on one of our own scenarios. Just this value for size, or science, or speed. Let's give it a little smaller, slightly larger. There are fewer free particles like now. They are all relatively close to our particle emissions. We go back outside. Let's disable our node and take a look. What it was like in the beginning. For example, to 100 frames. 100 frames. Let's take a screenshot. We put it next to it. Let's enable our node again. Then, simulate it to frame 100. Let's compare. You can see that a free particle like this one is approaching. We have a dense part of the emission source. Right, good. That's the whole principle. That I actually did an operation here. It is I who will mine. One of our generated. Density and VLM are also connected. Like this particle at the beginning. It is the densest. Then, we go through the sample of ours. Its dense parts will move closer to each other. Then some of the means I will do later. That is, the part that makes these particles dense. I don't want it to be displaced. Because I think its position is good. I don't need to let it go any closer. Then my overall particles will be less. Then we have this idea now. Take control. Places where particles are dense. That's equivalent to getting a mask. It is a place with high density. We make it move to 0. The place with low density. Then let it produce movement. So here we connect it. Here we are sampling the fluid type. Let's use volume sample. Just use the volume sample. Then add our peeling to sample. That leads to the third port. I use one of our scrap functions to connect it. We multiply them. Then the circle we enter like this. For example, here, I got the density of 100 places. I made it where the density was 0. We have a value of 1. Sink in like that. It means that we have high density. Then, one result of multiplying it is 0, because we map it to a new relationship. So we inverted this value. Let's jump out again. Let's take another look. Now you can see it. It has very few free particles. Then, we will take this grain. If the grain is changed to a little bigger, what it will be like, it's all blah. You see, there are almost no free particles left. That's pretty much ours, where the launch area is dense. Then let's control this density of ours. We made it a little bigger. We let it be 400 places. No displacement. Then, we have this grain. Let's make it smaller. So, in the end, we'll get such a form. Now you can control. There are many ways to do it. The first one is to say, back to our outer layer. To control our emission sources. It's black and white map. Then you can also give us a speed up review. Go to the direction size to change. Then, you can pass to the size of a particle or a meter to control the degree to which it gathers. Then, more of its densities can also be controlled here. For example, when you want the density to be as high as possible, no movement is generated. You will find its means of control very much. That might be compared to CCD. Then, there are not so many controllable parameters for it. That's inside Houdini. We have a lot of parameters at our disposal, one according to what you want, to generate some properties. Through some examples. Displacement, size, then the relationship of mapping can make some of the effects you want. Here I will give you a little experience, a setting of our project in my original film. Here I give a ball. The radius is 0.5. Then the frequency is given 1 T. Then give it a noise wave. I adjusted some parameters like this. I gave it no mouth. We clicked into our masked watch. I mentioned the frequency outside. Then the roughness was also mentioned. Enter the source size. I also mentioned the outside. You can take a look. It's all in this. Let's move on. This is the BI set. Don't worry about it here. Here is a multiplication given at that time. But it was not used in the later stage. Then here are some of the actions given to V. A multiplication was used. I didn't use the rebuke vector here. I'm here to do an operation on the whole. You can take a look. There is no direction in the size of V, separate to operate. That's also possible. Then this is a whole control. The source of our emission was then reduced. The reduction here is 0.5. After that, there is this sprinkling point. Then create the density property. You can take a look at its emission source. Then go to our PopNet. It is given scope 5, 0 point for a 之前. The size is given 1.5. Then there is our sub server. Enter our point work. It's all the same here. Then here my input. The source is 200. Then map to 1 to 0. Then here I give a function of power. Power function can be understood as yes. Contrast with the sliding wall. It makes the closer it is to a value of 1, the greater its strength. Let the closer it is to a value of 0, the less intense it is. This has minus shaped curve. The closer it is to 1, the higher its value. And the closer it is to 0, the smaller its value. It is to strengthen the effect of contrast. And here is also a result as a whole. Here's 0.6. And then that's our rough one. The principle is what we talked about earlier. What kind of form is it to turn out? You need to be patient. Good. Then, after our particle shape is determined, we need to cache it. The purpose of the cache is to say, it's convenient for us to change it. It needs to be resolved. Then we need to remove some of our unnecessary properties. Go for deletion. So why remove these attributes? Because there are some properties that we can't use later. Then, if it is informative, it will be stored on our point. Then if these things are not used, it will take up a very large amount of space on our hard drive. So we need to remove these things. Just use an attribute delete. Let's show you a signal here. Signal means to remove all attributes. Then we need to add some of the attributes we need. Just rule it out. Then let's press first. Pick one. We open this little arrow to our right. You can see that it is in all the attributes. That stores the properties we need. For example, the age. Then the id of an example. Then the health. Then we hold down the shape in front of each of our properties. Press and hold the 6th key on the keyboard. It will appear with a small arrow pointing up. Then this means that we have preserved these attributes of ours. That signal is to delete all. The one who marks these little arrows is to keep them. Don't let them be deleted. We can click on information to take a look. You can see that now only our age did live. There are also positions P and V also have these properties. Position P is built -n. It is definitely there. Okay, we use our fail cache. We connected it and give it a name. For example, calling. Here's a frame we cache. It is 1 to 250. That's a bit much. We give it 120 minus 5. So here we use the name of one of our nodes. Then this is a path for caching. Then pip is our project. It is stored in a path to the storage folder. Then it will be under this path. Create a folder called go. Then we will give it a folder called test layer. That's what we cache when the time comes. We'll enter this path. We tap our save to disk. It will pop up such a cache window. When it is cached, it will automatically turn off. Then we can use this of ours. Cache node to view it. Can be dragged at any time. Okay, then our particles have been cached. Then I want to give it some more properties. Then I think let's render it later. The part close to the source of the emission. Its particles emit brighter. Then I want to pass what? A relationship between black and white masking. Make a production through post minus production. How about generating such an attribute on our side? It can be seen that we have to generate retain here. 2 important attributes. One is age. We use a attribute triangle to define a mask. It is also a floating minus point number. Use our age. You must write our. This is the property that calls us. Remove with one of our health. Then it will get a value of 0 to 1. The meaning of life is how long the particle has survived. Because of a lifetime value of our previous particle. Have you seen it? The seed is 0.5. That's 2 to a 3. Then this is when every particle is born. It has already determined how long it will live. So how long has our particle been born? You see, we look at it from the very beginning. Then these particles. The outermost particle survived 20 minus 5 frames. It may be a particle that has just been fired. Then it just survived a frame. This should be well understood. By the time of our first frame, these particles are already there. Then it survived a frame. Then these particles are sprayed out again. Then they survived the second frame. The particles that just came out. Then it may be worth only one age. Then we can understand. That must be the particles outside. And the older it is, the older it will be. The farther away it is from us, the source of the transmitter. Then we use a node of our cover. Let's show us this property. Ran from attribute. We use our generated mask attribute. Let's take a look. You see it has been selected. Let's pull a comparison and take a look. Is this on a later stage? We'll have such a mask. Then it is displayed by color. What about this property that I want to call later? So how to generate it through our attributes. Then let's continue to write our attributes. At this point, we receive a new function. It's called a channel ramp. We directly let our mask go. Then go to one of our channel ramps. Then this function means generate a curve for this property of ours. It is convenient for us to go to a dynamic adjustment. The value ranges from 0 to 1. That's because our mask also has a value of 0 to 1. We can take a look at it through our spreadsheet. Let's take a look at this first. Hit the 2 double slashes in front to find our mask property. You can see that we drag a frame randomly. Observe our attribute. You can see this property. Its maximum value is 0.990 minus 9. Nearly 1. The minimum value also tends to be close to 0. So why is there such a negative situation? Although it doesn't matter in our case. Then I can tell you about it. Why is there such a negative situation? I go back to our first frame. You can see this emission source. It already has particles in production. It's always there. You see, it's always there. That can go back to our poll per net. Hence this launch motivates. That as long as we change it to a positive. Then, let's cache our cache. Let's simulate it for a while. Let's simulate it to 50 frames. Then, we disable our cache first. Let's take a look at our attribute again. The value of this mask attribute. That's the maximum is 0.990 minus 9. It's close to 1 unchanged. The smallest one has no negative number. So what does it mean from 1 to 5? 1 minus 5 indicates that it is in front of this value. It will be 5 zeros. It's 0.5. Then 19,000. Then this may be a, if you want to write. It could be 1 point. The back is a 1 minus 4. Oh no, what we get is a certificate. We don't recache it. We will use a good one that we cache. A cache of data that was previously used. Almost all of these values have no effect. If you're confused, that's like just now. You go and adjust it to the launch mode, then cache it again. We continue. What about this time? We have a mask attribute for us. Go for a mapping. Then we use our channel ramp. What about its writing specifications? You can watch phone to take a look. Then yeah, will let us go and name it. Then let's talk about one of our attributes to apply. It is a mapping of which attribute. Then let's get the name. We call it a ramp. What about the attributes? It is one of our masks. After writing, let's click on one of our tools. It will be map. Then let's use our colors to show it. We will restore this of ours. We only need to change it through our generator. Then we slide our slider. Then we can reverse it. Then choose one among us. Then you can add song. It's all possible. Then define it according to the scope you want. Good. Then our particle morphology is also well simulated. It's also done. Then we exported a property and set it up. Good. We did a good job with the two of us. Let's merge. This will show both of them. Then now we have this ball, because our particles are inside the sphere. So how do we make our model visible in the window? Then we can use an internal property. It's called, we use a. Remember that it must be capitalized. Let's make it equal to 0.1. You can see, we can see a particle inside us. The outside one. It is a transparent display. Good. We finished these 2 animations. Then let's do it next. We camera animation. We jump up. Then let's build a new camera. Our name is camera. Then I usually like to use 2 empty nodes to make cameras. Define 2 negative subunits for it. Let's sort it out. The camera is in the center of ours. Then we just need to select the second empty node. Let's give it a retracement. So that's where we're in control. This can control one of our rotations. This is very convenient. We will use this window of ours. Let's pull it a little bit. We did one. We hold down Ctrl plus 2. It will be divided into 2 perspectives. What about the left? Let's get into our camera perspective. On the right is a view of one of our special views. Then we can turn our cameras off. For example, let's turn back to 180 degrees. There is also one such one. It's a hole to look up to. It may be based on a rough animation of my original film. From here, from a close minus up, then pull out quickly. Then let's move our camera to a close minus up first. That goes through ours. Let's launch our example for a moment. For example, from the 70 minus 5th. Let's make a symbol K better than 120 minus 5th. Pull it out. Let's give it a little more K. Then we can animate. Preview from 70 minus 5 people. This is to go to the camera and the stationary. Such an operation. Then we can adjust our curves. We hold down the shift key. Tap it. It will pop up our curve editing window. Let's take a look at it later. Then let's start. I want it to be a very quick entry. After that may be a slow reaction. Take a look. It's almost like that. Then I want it to have some more up and down displacement. That is the value of KR displacement. Let's give it a K first. Well, I went to the 70 minus 5th formation. Give it a little more K. Then go to our curve editor. Find this piece of ours. So, do we let it get in quickly. After that, it ends slowly. Let's take a look at the hole again. Then we have this window on the left. That's one. An animation of a video camera. Then our main animation is done. These little balls around. Then you can do a little decoration. So, how to animate this ball? It's also very simple. We move on to our geo level. We use sphere balls on our side. Click on our window. We press Ctrl plus E. It goes back to our single window. Let's show one of our segments. Polygon is also used. Then, let's give it a little segmentation. Then, let's use another mountain node. That's a little big. We give it a little smaller. Then you can adjust the size of one of its sizes. Here you can use the animation that enables it. Play and take a look. Then, let's adjust the value. The higher the value, the slower it may play. For example, here I give it 5. Then, we'll give it a breakdown. With our loop mode, this is a moving ball. Then let's show it. Enter our camera. Then we move its position. Select our node. We hold the enter key. Then you can adjust the position of the ball. Then you can pass to. Control how far it is located. For example, here, I give it a little smaller. Here. Then, we also give it K from frame 70 minus 5. Let's first give it a K frame at the end. Let's first determine the position at the end. For example, the position at the end is here. Give it K well. And then back to our D. Let's move it this way. Let's see the whole thing. Go into our camera and take a look. Then, we can also adjust these curves of ours. And then ours. Transform node. Then this is it. These keyframes of our K. Here I also let it begin. Let's pull down a little faster. Let's take another mode. Can make it fast. Now it feels a little too consistent and not moving. Then we can make it faster. For example, you pull this value. Go let it. It's a little different from our speed. Several others. It's nothing more than you give it. Select all and hold out to copy. Merge together. Let's say you want to move it where you want to move it now. Go to keyframe it. For example, you want to move it here. Give it keyframe. Move it here. Keyframe. Maybe the three should be separated a little. For example, this one is here. Back to our very beginning frame. We link it all to our merge. Let's take a look. Here, good. Here are the keyframes. It is also from this area to move. Then come here. What about the little ball on the right? I also want it to come from the left. The location at the end of the day may be here. Good. Let's take another look. Then of course you can do this by adjusting it. Keyframes are staggered in some positions. For example, the external location here. You make it a little faster. Make it comfortable and a little faster. This way it creates a sense of staggering. For example, this will be very fast. These two will be a little slower. Let it have between speed. There is a sense of unevenness. Here we also adjust it. Adjust it appropriately. Good. That's probably the rate of animation. Then we can make it. The size of the ball is different. We give it a little smaller. Then give it a little smaller as well. Then change one of our random seeds. Then its animation will be different. Then some are fast and some are slow. Good. We've already wrapped up our entire animation part. We have the outside ripple here. We have a large ripple animation on the outer rim here. Then the one inside. There are also some animations of the small balls around it. Of course, you can do it according to what you want. I'll switch to one of my original projects. Go and explain the lighting on rendering. Bye. Thanks for watching.